class is, and I did that last spring, is at some point, probably I want to do it when we're halfway through the module, and I want to do it at the end. I'll ask you what you remember individually by email, and I ask you also, what kind of questions you have, or kind of feedback that, I'm really good at responding, because I can do it on my free time too. The reason is at this point we don't really have a whole lot of control over how you guys think between lectures, and we don't. The purpose of the class is actually that, to perhaps teach you a little bit to be self-sufficient in your learning. But I find it useful, and it's a suggestion that was made by other faculties for this specific subject we're teaching here, that just asking you guys, okay, so you listened to me for 6 hours. What exactly did you take home? On that, I think for the casting, really the general idea that it's easy to do. I don't want you to think of casting as something that difficult in the context of processing metals, because we do it anyway, right? But it's really mostly a question of cost if you're going to keep it as is, as opposed to going through extra processing to make it better. Now, there are exceptions, and I mentioned about investment casting. Casting components were the first one to be used in aerospace for load critical component. So you have castings for, the little coaster and things like that. Even some seat components, a lot of things in the little kitchen area, the bathroom. But when we talk about the primary structure, it's only about 10 years ago that there's enough demonstration studies done that if you do a very detailed investment part in titanium, for example, and the aluminum castings really don't get the properties that you would like and the consistency, but some of the titanium alloys are very hard to machine, and if you cast them, you get very similar properties just because of how the phases mixes and all that. So you get an as-cast structure that's very fine, as opposed to having these big dendrites. And that's pretty much the main reason why as-is TI-64, which is the most common titanium alloy, gets used now with not a high cost on the extra factor of safety. There's a little extra penalty that you have to pay on the stress level, as opposed to a wrought alloy of the same quality, but I think it's 1.25, so it's 25%. It used to be a factor of 2, and they managed to lower it down. It is based on having enough inspection work done to verify that there's no anomaly. One very particular thing with the aerospace is a lot of components are designed using a damage tolerant approach, which means that you just assume that there's already a crack in the material. So you're being a little pessimistic, and everything is predicted on you not having to worry about the crack leading to a failure until it reaches a certain size. And a lot of times you want that growth of the crack to be so slow that even if you miss it in one inspection, you pick it up in the other. That's what we were discussing. It's not to say that each inspector is not accountable for for finding or not finding it, but it's a very, very specific industry, and I guess I'm just trying to expand on the idea that it's not all castings that are low quality or low cost components. You can have a very sophisticated casting. Another example of sophisticated casting is the moment frame connections. In earthquakes, large buildings will have, it's mostly applicable to California, but in different regions in this country, we have requirements in the building code that says if I have more than, 5, 10 stories and certain characteristics, I need the building to really stay up, even if it's a earthquake of magnitude, whatever, 6 or 7. And the way they do that is on the cross beam that link different columns, they'll put a little bit of a kind of a deformable component, a damper. So when the earthquake comes and one column tries to lift with respect to the other, you use essentially the yielding of the steel as a shock absorber, so things don't go too far. Because it's essentially an impact, and to the extent that instead of just having a spring here, you have the material stretching, it's damping. It's a damping factor. So these components, they need to be designed in a way that they're flexible enough, and say they're bolted in place or welded in place. You don't want the bolts to break. So they need to have some kind of a weakness, internal weakness, as opposed to a weakness about where they join to the beam. And it's because of the complex shape, they make them out of casting these days, steel casting. It's the only real kind of structural steel casting in large quantity that I've seen. Not that there are not others, but we talked a bit about the aluminum castings that really had the advantage to be kind of a low temperature process. I showed you some videos. We were in the shop, and you just do it really quickly, right? You just inject it, you melt it, it's all hot, transfer it, boom, I get a part. Yes?
In this one, the difference between the columns and the cross member is basically these ones are rolled, and this one you are saying is cast.
Yeah, the little reinforcement, the damper. Yeah. They call them moment frame connections, if you want to study on that. It's a pretty specific application of a casting.
But the vertical ones are generally rolled.
Yes, yeah, rod products. Yep. So they'll look a little bit like this one. We'll go over that. That's right. Okay, so what we're trying to do, if you remember at the end of the last lecture, we talked about the stress strain curve because I wanted you to think clearly. We're moving on. We're starting to take that casting and deform it into a material, a rod product, just like this column, that will be a lot more resilient when there's a load applied. So you get rid of all the dendrites. You have a lot going on that really helps you. So the stress strain curve, just to make sure we're all on the same page, I'll just use deformation. You can express it any way you like. This is the elastic portion. This is the springs that we were talking about. And from here on, the main thing is what happens doesn't come back to you right away with metals. And we'll do plastics today as well for this behavior. So you go up here, and essentially you're stretching the material when it's the tensile test and tension. You reach a certain level where you have your neck. We talked about that. And then you go to your failure point. That is due essentially to having a very complex triaxial state into the material. And it is something that I do want to emphasize, that from the time you form a neck during the tensile curve, you have a zone in the center or wherever it is that your neck is forming on the specimen that's reduced in size. And what it is, if you think of it, the way this material carries stresses now has a certain directionality. So I'm showing kind of stress line pattern here into the material. So probably you'll see that I'm stretching it from different directions, and we call that stress triaxiality. When we have stress triaxiality, so this is also happening in the other direction. It means that there's a lot of tension in the material. And tension is what causes the formation of cracks. But before you have cracks, if we're talking about steel, we always have these little microvoids. So the microvoids are kind of the precursor to a crack if it's behaving in a ductile way. And without going into the detail, what you will do to start this failure here is you have your material and then you have little voids very nicely distributed close together. And then eventually the amount of material left between the voids is so small, it stretches and it breaks. There is nothing here about the crystal separation or anything like that. It just doesn't happen. There's so much ductility in normal ductile behavior that everything is driven by the flow of material. So the flow of the material causes the formation of very, very small void because you have this tension in three direction. Those voids grow to a certain size, and then you start the crack. Now, when you started this, the time that this starts linking, then everything will shatter on you. And the cone and crack is the result of starting a crack like this, kind of a real tension crack, and then you can move into a shear failure mode, and that's why we get a cone cup on a typical failure. Let's see if this is. Yes.
For which material is this curve line?
For which what?
For which material? It's not steel, right?
This is steel. Yeah.
Steel?
Yeah. Sometimes that's not what I'm looking for. Oh, this is going to be complicated. All right. We talked last time that one issue with this curve is it defeats our intuition. It's saying that the material is weakening, and it's not the case. The reality is when you correct for everything, that the yield continues to go up where the material is. So if you were to plot this type of stress versus strain in the zone of the neck, it keeps going up. And there's actually a relationship that allows you to do it. These are the equations to essentially take the normal engineering stress strain curve, which is essentially the load divided by the original contact cross section to make it a true stress strain curve. So we're not going to emphasize on that. What I want to do now, that we're on the same page here, is expand on what happens in the material when you deform it. Everybody's heard of dislocations? Good, good. The dislocations are there in any crystal, even from when the crystals form. The main thing that I want you to keep in mind, and you probably have seen these analogies, I won't emphasize them more than we need to. You have the carpet, and then you make a little fold on the carpet, and that will allow you can translate that fold back to the other side and become longer. You just push on it and move that wave that way. So that's the principle of the dislocation, that you have a small change. It can be just an extra half plane of atom in the crystal. So that extra half plane, you can just move it across and cause a permanent shear deformation. So everything happens in shear in the material. The only real aspect that I think may help your intuition with the dislocations is they go in different directions, along different planes. If we're talking about steel, for example, we have 8 different planes in space where these dislocations are equally likely to travel. So given that, there will be intersections between them, and that's really a key aspect that explains why we have an increase in strength as we deform. The dislocations start interacting and they multiply. And the only reason that I think you can remember that is it's not just a carpet. It's so many carpets in different directions that if you try to avoid one movement not interacting with the other, it's not going to happen. So I'm showing here just a simple Frank Reed source where from only one dislocation segment. So the way the greatest majority, like 99.999% of the dislocation in the material are full loops. So in one side of the loop, it'd be, well, I have an extra plane, half plane. On the other side, I'm missing an extra half plane. So I just essentially took a plane of material and I just moved it a little bit. And now I can move back and forth very easily through it. So over here, because it's a loop, there's nothing that says the entire loop is on a single plane. Plane of deformation do intersect. So if I have a loop that I drew it, I intended for it to be in this plane, it will cross eventually and be able to move in another plane. So that's where that segment comes from. The reason the segment is held here is the other part of the loop is on another plane. So we start from here. It's held at 2 area, and under the load by shear, I'm able to expand this small section of the loop all the way until that it start touching with each other, and then I form an entire new loop. It's considered the most common way of multiplying dislocations. And when we're talking about multiplication, we're talking about thousands and thousands of times more than what you had in the original crystals. So that's why we have this. It's the only reason. So you'll have this strain hardening on a pure crystal. The one place, if you want to be very serious with me, on a bulk metallic glass, you don't have it unless it crystallizes when it's deforming. So if I just take a bulk metallic glass that doesn't have a crystal structure and I want to deform it, typically it'd be pretty flat. If it does have hardening, which does happen a little bit, so it will be deforming at just a certain point and then break out here, maybe 2% strain. Something's going on. I'm reaching a point where I'm forming some crystal, and that itself causes me hardening and increasing my shear capacity. Any questions about that? I think I covered. Yes?
What's an example of that kind of material?
The bulk metallic glass? A Victoloy, I worked on these a lot. So nickel rich. Typically, to make a bulk metallic glass, you need 2 or 3 elements, and you're looking at putting 20% of something that doesn't like the other. So if you put nickel with an atom of a completely different size in proportions, and you do it, if you do it slowly, I think you can probably intuitively think what's going to happen. You're going to form one face of one and one face of the other. If you just cast it super fast, then it stays as an amorphous, kind of as a liquid structure. And it's an interesting engineering challenge to make. But for this reason, that it doesn't have hardening, you're essentially faced with very high cost and very low forgiveness in terms of being able to take and stretch a little bit in service. So it's not going to be used for making an airframe anytime soon. It doesn't matter that it's got a very high yield strength if it behaves a little bit like glass when you deform it.
What is it used for?
Very little. I don't know of any real application for it in terms of structural material. I think it has application in the kind of semiconductor industry, I'm sure, but even that is small quantity. I think it's just generated a more scientific interest than a real industrial push. So we talked about this, that the dislocation is an entire loop, and I actually think I realize more with time that sometimes just describing it is easier. Here, I don't know if this helps or hurts your thinking, but it's probably the last time that in this module that you'll actually see the name of the two types of dislocation. I don't even know. It helps a little bit, to tell you the truth. So the edge dislocations are the one here that have the extra half plane. And the screw dislocation is just really the twist of where you start making that switch into the half plane. Perhaps the only place where you look really nice and you look really educated, if you remember which one is which, is in the steel. When we'll talk about brittleness of steel at low temperature, it has to do with the screw dislocations. So remind me to cover that. And one reason is the screw dislocation can move plane more easily normally than the edge dislocation. The edge dislocation, and I'm here. I got an entire plane to deal with, so I can't move around very much, and the screw is more able to switch from one plane to the other normally. Yes?
By normally, do you mean regularly or
At the high temperature. I mean at high temperature, when it's not an impact condition or cold temperature.
as
Yeah.
opposed to like perpendicular?
Yeah, no, yes. Thank you. Yes, any questions? All right. So what happens then? We have a lot of dislocations. When we drew, I'm going to take this one now and call it the true stress, true strain curve. We know that it's a little more steep as we correct for the difference between the engineering strain, the true strain, and the same for the stress. And this is where our UTS lies. It's not the point of higher capacity. The capacity keeps going up. And then what I started talking about in the last lecture was, is it going to stop eventually to an asymptote? Well, very, very close. And what I said, if you remember, I said that somewhere, 200-300% strain, you start getting so many dislocations that they will force themselves to recombine with each other, and you reach an equilibrium in the amount. In just a rolling operation, it doesn't lead itself necessarily to a very nice looking structure under the microscope. But when you do the cyclic deformation, this is what I'm showing here, you can get these different zones where you have very little dislocation, and all the dislocation are lined up in walls. And what it is essentially a natural way for the material to segregate an area of activity for deforming and an area of recovery for deforming. So the recovery is where you take two dislocations that are opposite sign, they come back together, and there's nothing left. It happens even at ambient temperature at these very, very high strain, but it's because all the dislocation, there's so many of them, they get so close that they do interact with each other. Now, we will talk in deformation processing about the fact that as you keep increasing the temperature, it is more easy for these recombination to take place, and that's called recovery. Anything on the dislocations? So the black spots is where you have a lot of dislocation. This is TEM images, so transmission electron microscopy. This is only 1 micrometer, so you're looking at a very, very fine layer of material, and there is essentially less transmittance of the beam in an area where you have a lot of dislocation. It gets scattered a lot. So it's not an individual dislocation. It's kind of telling you an idea of the density of dislocation in the crystal in that area. That's pretty much the closest you can get to seeing dislocation with that instrument anyway. There were other ways. Okay, let's go back in terms of practicality. This is only 200 micrometers, so this is about 1 millimeter. By eye, I may be able to see grains, and I'm going to distribute this for you. These are samples that were subjected to different heat treatment. Oh, you got the temperature right here. At the intermediate temperature, the 600 degrees, especially if you look here, even though you start with a very, very smooth surface, you can touch this and feel that there had to be some very, very large grains in the deformation. These are tensile test specimens to explain what we're saying. So there may be some grains there that are, what, 3 millimeters maybe? You can shine it with the light. Yeah.
That just happens when you pull it.
Yeah, they showed up when you pull it. Yep. So the quick story on those samples is they were all sheets coming out of the mill. And what we did as kind of an academic exercise is to heat them up, to sort of heal them, to make them recrystallize, recover, depending on the temperature. And there's this intermediate temperature where some grains grew very fast compared to the others. It's something that you do want to avoid. It happens, unfortunately, a lot on kind of pure metals. So if you are a manufacturer of aluminum conductors for the electrical industry, this is a big problem because you want a pure alloy, but a pure alloy means that the grains can grow very easily when you heat up the aluminum. So this particular case is just to we're looking here at a section of this before it was recrystallized to the high temperature. So this is the 400 degree. It's a very fine structure. You see the grains are these larger features. So you have one here, and inside the grain you just have twin boundaries. So maybe I think the good advantage is the twin boundaries allow us to see better the boundaries of the grain here. So we have one grain here that can easily be identified. We have one here. We definitely have, well, what is this line? I don't know, because the twin continue, the twin boundaries, so maybe this is a grain here. I think there's nothing like saying it. When you see this, you're like, oh, wow, maybe this is going to break right there, right? Generally not. It's not because that you have grain boundaries that when I deform and I start forming the microvoids, what we were talking about over here, there's nothing to say that the voids are going to start forming at the grain boundary. No. So you don't have to worry about that in the general case. If there is an effect of the environment, which is not, can't go too deep in there, but if there is, say, a high hydrogen environment, something that is very corrosive, you can have a situation where then these small atoms are going to go in the grain boundary preferentially and cause a different kinds of failures. So it is possible, but in general, especially in our context of forming material here, we don't want to consider that a problem. It's actually an advantage, and we'll go through that as we move forward. So the grains typically affect a lot the strength of the steel or the metal, or bless you, or the material that you're dealing with. Here, what we have is the hardness of certain metals as a function of the inverse of the diameter of the grain. So essentially, the grains are getting smaller going in this direction, and they're getting into the nanometer range. So this is a topic that's been of very high popularity in the course 3 and other departments for 10 years, 20 years, making nano everything. And you have an image here. They say nano, but sometime when it started anyway, it was about 20 nanometers for metals that you could make, and then they got much better and they were able to make 3 nanometer grains. The concept there, because I'm going all the way from very general here to specific, between a grain that's almost a millimeter, 100 micrometer, and then nanometer range, what you do is you force the entire system of dislocation interaction, like all these Frank-Red source and everything going on in the material, you constrain it to a smaller area. Because these dislocation, they don't go across the grain boundary very well. It's a high energy zone, so they tend to stay within them. So perhaps for you, that's a kind of an intuitive way. And a lot of people have come up with different models of why smaller grains give you higher strength. But in a simplified way, it's just about if you're going to operate a number of Frank-Reed sources, you need space. And when you're down to 5 nanometers, you just don't have enough. You really don't. So the way these smaller crystals are found to deform a lot of times is a dislocation initiating at one interface and traveling through. It's kind of the opposite. It's okay for you to remember this, but remember that it's not generally the case, that it's really when you're very, very small. So what I said doesn't apply for the carpet concept, kind of applies to a very small nanocrystal because it's just one event at the time. Now, I do want you to know, when I tested these at high strain, they recombine because there's so much energy of interface involved in having these small grains that as you start activating and essentially inducing diffusion to deformation, the grains grow very quickly. And to me, that was a problem in terms of thinking of them as really good for wear resistance, for example, because the surface will get the deformation and become softer as opposed to becoming harder. If you want a good wear surface, you take it, and as it gets hammered, it gets stronger. That's good, but if you take it hard and it becomes softer, it defeats the purpose. So that's something to keep in mind. Now, what I want to do now is go back to how we roll steel. I think we have all the concepts to do it, and we'll do it on the board. I think we discussed we have the billet first. It's got a little chill zone. Then it has more of the elongated or columnar grains, and that can include the dendrites typically, although the dendrites in a lot of processes do get broken down. So there's nothing to say that it's just one grain. You can have multiple of them. And then you have kind of the center where everything ends up cooling, and that's where you get porosity. That's where you get more concentration of your alloying elements down here. When you start thinking about processing this, the worst you could do is pull on it because you're going to start creating cracks. So all the concepts that we've talked about, deformation, going in shear, and going into 100, 200, 300%, that's all good if you keep compression as the main source of action. So there are a number of ways. You can have 4 rollers, just guide rollers, push rollers, but ultimately you are flattening the product gradually. Now, you could go pretty fast in doing this if you wanted in terms of speed because it's really hot. One reason why it may take, it may take up to half an hour to go from the original billet to something that be, say, 1/4 inch in size. So if this is a foot and this is 1/4 inch, it could be a little longer. What it is you want all these alloying elements, the extra carbon, the extra manganese, everything from the center here to go and diffuse back to the original surface. So one reason for hot rolling is breaking down the casting structure, but a related aspect is to induce diffusion that homogenize the chemistry as well. So if you're going to go and do that, what happens to the grains is always an interesting question. So the grains will be deformed. So say I start, and I'll take one grain at a time. So if nothing happened to the grains, in other words, if I don't eliminate grains or create new ones, then they'll stretch up to a certain point. And that's fine. What's going to happen also is the density of dislocation is going way up. In a typical hot rolling process, you have recrystallization taking place. So what does that mean? It means that I'm getting to a point where there's so much dislocation here in that one grain that's deformed that if I start from the boundary in making a new crystal from there, as I make the new crystal, I just eliminate all these dislocation in the next one. So from here, I can essentially have nucleation just the same way we saw it in class and start a new grain from here, a new grain from there, a new grain from there. And as they get to a certain size, they grow faster, so they'll take over the entire space. So say I'm done with, I made 4 grains out of one here. I had another one right over here that I missed. So that is the recrystallization process. The reason, the driving force is so much internal energy in the grain, and you do need temperature, right? So you do need all that thermal activation to be there to help you. What it allows you to do is get rid of that elongated structure. So I don't want you to think, oh, well, my grains are all round, so, you know, this was not deformed, this was not rolled. It has no real relation. There's so much that happened from the time that you had the casting to your final product. So I do want you to keep that in mind. And there is a certain level here, if we look at essentially our flow stress is going to be very sensitive here. So we have our stress level and we have our strain, and ultimately we're looking for a material that, say, it's accumulating deformation, it's starting to deform, and then eventually, oh, I'm starting to recrystallize, oh, I'm hardening too, and I'm recrystallizing. Guess what? Reaching steady state. It does happen in the rolling process that essentially the flow stress for deforming the material becomes almost constant because you keep having grains that are this way and you have grains that are this way and then everything in between, and it just goes on and on in the entire space. It's excellent in terms of diffusing the atoms for segregation, and it helps with the processing of the material. So what we just discussed is the sequence of getting to that constant flow stress. When you're here, of course this line may be going up or down if I change my strain rate or if I change my temperature. So I think that is the reason for doing all of this work, the deformation processing. What's the problem? Because there are problems. What do you think is the problem? If I keep doing this, and let's say I start from something this big, and I end up with 1/4 inch, and then I'm going to go to a little bit to the extreme. Let's say we go to 100 micrometer, which is doable, but it's getting small, right? Bifoils like that. Any idea? Yeah, that's true. That's true. One thing we haven't talked about, this is a little unfair because I'm talking about, the metal, the grains, all that. Life is good. Inclusions. Inclusions are present in most engineering alloy. The reason is it'd be very expensive to make them without them. And in general, we can get by with inclusions. But the inclusions are essentially non-metallic. So say you have aluminum oxide, you have silicon oxides, all sorts of things that end up interacting. And some of them we generate. We add aluminum in the process to capture the oxygen, for example. So we make a good steel, but it forms these little, ceramic piece, essentially, if you want to think of it that way, that are part of that ingot here. So say I have a piece here that's the non-metallic. Well, it's not going to diffuse because it's stable at the temperature that we're rolling. It likes the way it is. So the only thing you can hope for is that it breaks down in smaller pieces. That's kind of ideal. If it does, then you hope that when you're very small that the inclusion remains significantly smaller than your product thickness. But there's no guarantee to that. So that's where if you're looking into especially aluminum alloys, the problem with aluminum is it's so sensitive to oxidation. We know at ambient temperature it's always oxidized. When we cast it, it does tend to oxidize a lot as well. So when you do this entire process with aluminum, you end up with a lot of inclusion in your material. And if you're trying to do a small wire, it'll break on you because now you have essentially a hole, practically speaking, in the material in an area that you don't want it. So I think in the context of advanced manufacturing, it's really important because there's a medical company that had us do some material selection for them for a device for surgery that was really small. And there wasn't an easy way to avoid this unless you ask for a very specific piece being made for you that doesn't have these inclusions in the first place, or that makes it in a type of inclusions that will break down in very, very small quantity. So that's probably a drawback of going from very big to very small. The other drawback, we mentioned cost, and that is very true. You also, as you go and keep it hot at high temperature, you do form a scale on the product. So there's going to be a layer here that is oxidized, and you can clean up. That's a good point, but then you start adding cost again. So most of the time, if you bought raw products, it's not shiny steel. It will get shiny if you grind it, but the surface of it is a scale from the oxidation, because you don't want the entire mill to be in vacuum or something like that. Okay, so we all agree on that. So so there are two aspects. That's good. So one aspect is if you sell the product with the scale on it, doesn't rust as easily, so it looks just about the same whether it was left outside or not. I mean, you even have a lot of products, sometimes they'll be shipped oily to make sure that they get there without rust on them, and then the customers start complaining about it. So it's just part of kind of knowing. I always thought, and probably that's the reason I've spent so much time at your age studying material science, is you can really figure out what's going to be the problem, and how to avoid it sometimes from doing this. If I want something really thin, There's nothing wrong with doing it with fine powder sometimes, because you avoid all these problems. It's already plain gut. You can screen the powder in powder metallurgy to not have the big inclusions. Yeah, so it really does have advantages depending on what you're trying to do. Okay, so
Does it add a lot of
Yep.
cost to turn it into the powdered form?
yes, so, and there are a lot of, so atomization is very frequent, so you essentially jet the liquid metal into a spray, and it will get oxidized a little bit in the process. So now you have to process that powder to get it clean again. It's not the only way. There are many ways to make powder at a reasonable cost. So maybe your raw material is what, 2-3 times what would be a raw piece of steel. If you're not too, difficult on the quality or the size distribution that you're looking for, and the reason is there is a high demand. I don't know. One of the main use of steel powder is to put in cereals. In terms of money, because you need iron supplements in cereals. So they take the melted steel and they go through this atomization type process. They like 3 or 4. It's been way too long. This was like 10, 15 years ago. I went to a shop that was doing it, and they needed to get a special certification for FDA approval. But yeah, I mean, if
Steel in your theory.
yeah, particles.
Meaning the steel cutouts, am I right?
They're not cutouts, but they are kind of flaky because they once you made them, if it oxidized when you clean it up, it becomes a little bit of a flake, and the specific process for making cereal is different than making a part. The part, you kind of like the idea of having round pieces. They get more compact easily together, and you get a higher press density. The other one, you get a higher press strength because everything gets tangled together. So both of them are used, but the one this flaky one just goes to a lot of cereals and other food. I mean, whatever says there's iron supplement, it's going to need to come from somewhere. With inclusions, perhaps. That's a very good question. So the last thing I want to say, and this came up, I have a project. I'm sponsoring some students to do some testing, and they got very surprised by this, but it's really true. If I take a block of steel, I'll take aluminum. Let's do, because it's more relevant. Looks good, right? Well, I can machine it any way I want, and I'll get a certain product. Now, as a result of the inclusion in aluminum, if I'm looking for the fracture toughness, so say I make a pre-notch here and I pull on it, if this plane of the crack is the rolling plane, my fracture toughness can be at least half, just half or less than half what it would be if I do it transverse to the rolling direction. And it's not so much the yield strength and all of that and the grain elongation. No. It is the inclusions. So it does play a big role. And even in steel products, a lot of times, if we make a T-connection, so I have a piece of steel here and I have another one here, and I weld, you wouldn't think that'd be a problem. You'll think that maybe this is a weak link. But sometimes we have to do a special calc to make sure we won't have a delamination of that piece here, just because of the lowest resistance in the plane that we have inclusions. So it is a real reality. So we call it true thickness stress. When we have high stresses in the thickness direction, we have to be careful in essentially lowering the allowable stress for that. So hopefully you guys realize that the formation processing is important.
Do inclusions like localize in any certain Z depth through the thickness, or it's like evenly spread throughout the thickness?
They tend to be more in the center because they don't have this diffusion need, and that's a very good question. So right down the center line of a wire is where you expect the biggest pieces. Yes, that's really true. And I guess it's an advantage, right? For most cases. Yeah. It's an advantage in terms of trying to get a crack on the surface if you don't cut it. Now, if you cut it in half, now you have the problem on the surface. So it's just, and I've seen it, so that specific issue of the inclusion being a center comes in pre-stressing wires. You take pieces of steel that normally here for our stress strain curve, we're looking at 35 KSI, but you can boost that up to 200 or 250 just by cold working the steel. But when it snaps, it's always at an inclusion. It's just, and your strength becomes dependent on how big that inclusion was. That's it. All right, guys, I'm sorry it took a couple of minutes more, but my pleasure. So this week, I'm also teaching tomorrow and then Friday. Professor Eager is going to be here Wednesday and Thursday. I sent an email announcement, and I'll try to do that every week now, so you guys know.